3/3/3I Atlas has once again left scientists stunned by what has been observed around perihelion, turning a routine watch of an interstellar visitor into a growing scientific and public fascination. As the comet neared the Sun, astronomers began noticing changes that did not fit comfortably within the patterns normally seen in cometary behavior, and each new dataset seemed to add another layer to the mystery. Among the most widely discussed anomalies were an unusual non-gravitational acceleration and a striking blue hue, features that together challenged expectations about how a natural icy body should look and move when heated by solar radiation. Yet perhaps the most contentious aspect of the entire episode has not been the comet itself, but the way its most detailed images have been handled. According to accounts circulating in the astronomical community, the sharpest view of the object was captured on October 2nd, 2025, when the comet passed within roughly 30 million kilometers of Mars. The image was taken by the HiRISE camera aboard NASA's Mars Reconnaissance Orbiter, a system renowned for producing extremely high-resolution pictures of the Martian surface. The timing, however, was awkward. October 1st, 2025 coincided with a U.S. government shutdown, and while the observation proceeded the next day, the data were never publicly released. A researcher who contacted HiRISE's principal investigator reportedly asked to access the dataset directly, offering to leave any press coordination for later, but received no answer. Weeks passed as the comet continued to display never-before-seen characteristics, leading to the question echoing through online forums and even some professional circles. What exactly is NASA withholding, and why? The debate intensified once orbital analyses revealed that 3I Atlas was not traveling solely under the pull of gravity. Instead, its trajectory showed abrupt and sharp deviations that implied an additional force. NASA data describing the object's motion indicated two primary components of this non-gravitational acceleration: a radial push away from the Sun on the order of about 135 kilometers per day squared, and a transverse component of roughly 60 kilometers per day squared relative to the Sun's direction. Such figures were extraordinary because while small non-gravitational effects are sometimes observed in comets, typically caused by jets of evaporating material acting like tiny thrusters, the magnitude and suddenness here appeared unusually large. This prompted renewed attention from Harvard astrophysicist Avi Loeb, who has become well known for urging scientists to consider unconventional possibilities for interstellar objects. Loeb argued that the measured acceleration could, in principle, be consistent with some artificial energy source or an internal propulsion mechanism, a signature not explained by gravity or standard outgassing alone. His suggestion did not claim proof of engineering, but it widened the interpretive frame, inspiring some researchers to rethink whether a purely natural process could account for so much force so quickly. If the acceleration were the first puzzle, the comet's color became the second. Comets approaching the Sun often redden as dust and gas scatter light, producing a warmer tint or even a golden halo. 3I Atlas, by contrast, shifted toward an intense blue. Blue coloration in cometary coma is not impossible. Certain molecules can fluoresce in blue wavelengths, but the suddenness and prominence of the hue in this case stood out. Loeb described the blue shift as yet another anomaly, characterizing it as potentially compatible with very high temperatures, unusual chemistry, or even artificial illumination, though other scientists emphasize that exotic natural explanations must be exhausted first. The intrigue deepened further when observers noticed a dramatic increase in brightness. On October 28, 2025, just before perihelion, reports indicated that the comet brightened much faster than models predicted, reaching an apparent magnitude near 9 at closest approach, comparable to stars visible in small telescopes. Amateur astronomer Waracha Bunpla reportedly spotted the brightening in imagery from NOAA's GOES 19 weather satellite, and noted that its luminosity was comparable to stars around magnitude 11, making it one of the more prominent objects in the sky at the time. Most comet specialists pointed to a plausible explanation. Intense heating near perihelion could have triggered major outgassing, causing the release of dust and gas that reflected additional sunlight and made the comet flare unexpectedly. Still, the speed and scale of the brightening, occurring alongside the acceleration and color change, fueled speculation that something more than ordinary sublimation might be at play. Some hypothesized that an internal heat source could contribute to the flare, though the idea remains far from established. Meanwhile, the continued withholding of high-resolution imagery remained a sore point. The Mars Reconnaissance Orbiter's October 2nd images were described as 3 times sharper than previous Hubble Space Telescope pictures, potentially offering critical clues about the comet's shape, surface activity, and the structure of its coma. If released, such data could allow independent teams to model jets, estimate mass loss rates more accurately, and test competing hypotheses about the source of its acceleration. Loeb publicly criticized the decision not to share, arguing that suppressing data slows science and wastes a rare observational opportunity. Others, more cautious about attributing intent, suggested that bureaucratic delays, mission priorities, or data processing backlogs during the shutdown might explain the silence. Yet the longer the delay continued, the more it amplified public distrust and encouraged conjecture about concealment. As 3I Atlas rounded perihelion on October 29, 2025, telescopes and space observatories recorded still stranger details. NASA's Stereo A spacecraft and ESA's SOHO mission observed an unexpected glow surrounding the comet, extending beyond its visible tail in a way that suggested energy or gas emission outside normal patterns. Ordinarily, cometary tails form as solar heating sublimates volatile materials like water, carbon dioxide, and carbon monoxide, producing a stream of dust and ions pushed away from the sun by radiation pressure and solar wind. In this case, however, the tail appeared diffuse and erratic, with emissions not confined to the standard anti-solar direction. Observers described anti-tail behavior, where materials seemed to extend sunward, a phenomenon that can occur in some comets due to geometry and particle size effects, but seemed unusually pronounced here. The gas release patterns also looked scattered and unpredictable, implying either a complex rotational state, an irregular surface with multiple active vents, or some other force shaping the flow. The comet's trajectory added one more statistical oddity. Rather than arriving on a random inclination, 3I Atlas's path was aligned closely with the plane of the planets. Analysts estimated that such an alignment had only about a 1 in 500 chance of happening by random interstellar arrival. On its own, that probability is not astronomically impossible, but when combined with the acceleration, color shift, brightening, and tail anomalies, it added to the sense that this object was a special case. A few astronomers floated the idea that the orbit looked too neat, though most emphasized that low-probability alignments do happen naturally given enough visitors over cosmic timescales. Still, the question lingered in some corners of the community. Could the comet have been deliberately directed into the solar system, perhaps as a kind of reconnaissance or purposeful flight? Such claims remain speculative and controversial, but they illustrate how far 3I Atlas has stretched imaginations. As data accumulated from multiple observatories, the emerging portrait was of an object with unusually strong outgassing, far more powerful than typical comets, which tend to expel gas and dust in more predictable, smooth curves as they warm. Instruments aboard Stereo A and SOHO recorded emissions extending farther and with greater intensity than expected for a simple icy body, implying either vast stores of volatile material, an atypical composition, or internal heating processes not commonly seen. The blue hue, often associated with higher temperatures or distinct molecules, suggested that the coma might contain species rarely dominant in other comets, or that the energy environment around the nucleus was unusually intense. Estimates of the comet's size and mass also fed the narrative of an extraordinary visitor. Based on brightness and activity, some analysts speculated that the nucleus could be comparable in scale to a large city, perhaps as big as Manhattan, with a mass on the order of tens of billions of tons. Those figures are rough and depend heavily on assumptions about albedo, dust production, and geometry, but even conservative estimates implied a far more substantial interstellar body than earlier visitors like Oumuamua or Borisov. A large, active object of this kind would naturally sustain stronger outgassing, which in turn could explain some portion of the non-gravitational acceleration, though whether it can fully account for it remains an open question. As the comet moved behind the Sun from Earth's viewpoint, scientists prepared for the next phase of observation. In the coming months, once the comet re-emerged into night skies, ground-based telescopes were expected to regain direct lines of sight, enabling more detailed spectroscopy and imaging. Researchers hoped to measure the chemical makeup of the coma, identify dominant volatiles, and map the evolution of the tail to determine whether the strange perihelion behavior was a transient reaction to intense heating or evidence of deeper structural complexity. Particular excitement centered on planned observations with the James Webb Space Telescope. As the most advanced infrared observatory available, JWST could detect molecular signatures inaccessible to optical telescopes, potentially unveiling uncommon compounds or temperature structures that might clarify the source of the blue hue and the nature of the outgassing. High-resolution infrared imaging could also constrain the nucleus size and thermal properties, offering decisive tests of competing ideas about internal heating versus surface sublimation. For now, 3I Atlas remains one of the most astonishing interstellar objects ever recorded in the solar system. A comet whose rapid brightening, vivid blue shift, striking non-gravitational acceleration, and peculiar emission patterns have forced astronomers to confront how much they still do not know about visitors from beyond our stellar neighborhood. Some of its features may eventually be explained by unusual but natural processes, odd chemistry, delayed venting, fragmentation, or extreme volatile content. Yet the combination and intensity of anomalies make it a standout case regardless of the final interpretation. The controversy over unpublished high-rise images has only magnified that status, turning a scientific curiosity into a broader conversation about transparency, institutional caution, and the fine line between responsible interpretation and sensational speculation. As the comet continues outward toward the depths of space, it leaves behind an unresolved but thrilling question. What is 3I Atlas really? Is it simply a rare natural traveler from another system whose properties happen to be extreme, or is it something that will require new physics, new chemistry, or new ways of thinking about how interstellar bodies can behave? Whatever the answer, the episode is a reminder that the universe routinely surprises us, and that each unexpected visitor can redraw the boundaries of what we consider possible. Beyond the immediate spectacle of 3I Atlas's perihelion passage, what makes this episode so sticky for scientists is how it collides with the usual toolkit for understanding comets. Normally, when a comet shows extra acceleration, researchers can trace it back to asymmetric outgassing. Sunlight heats patches of ice, jets form, and those jets act like tiny rockets. The math is messy but familiar. With 3I Atlas, the scale and timing of the accelerations felt abrupt enough that standard jet models struggled to reproduce them cleanly, especially if the object is as large as preliminary estimates suggest. A massive nucleus should have more inertia, meaning it takes a lot of sustained thrust to shift its orbit measurably. That pushes scientists toward two possibilities that are both interesting in different ways. Either the comet has an unusually efficient way of venting material, like volatile reservoirs buried under a crust that cracked open suddenly, or our assumptions about its mass, density, or shape are wrong. If, for instance, the comet is far fluffier than typical bodies, like a low-density rubble snowball, smaller forces could move it more dramatically. That kind of structure would itself be a noteworthy clue about how interstellar comets form in other systems. The blue hue is similarly double-edged. On one hand, blue coma can occur naturally when certain gases dominate, such as ionized carbon monoxide or other carbon-bearing species that glow strongly in blue wavelengths. On the other hand, comets this close to the Sun usually produce lots of dust, which tends to wash the color toward white or yellowish tones. A sustained blue appearance implies the dust-to-gas ratio might be unusual or that the gas composition is skewed towards species that fluoresce under intense solar UV. If that's true, 3I Atlas could be carrying a chemical fingerprint of its home system, materials that were abundant there, but are rare in our own comet populations. That's exactly the kind of thing astronomers dream of, because it gives a direct sample of another star's planetary nursery without needing to travel there. The brightness surge, too, is not just a fireworks show. Rapid brightening can signal fragmentation, where a nucleus sheds chunks